Hi everyone, today we're going to get started on chapter 8. So in chapter 8, we are going to look at the reaction of alkenes. So because single bonds are more stable than pi bonds, most common reactions of double bonds transform the pi bond to a sigma bond. So we looked at the bond strength in a previous chapter. So when we look at a carbon sigma carbon bond, the bond strength is approximately 83 kilocals per mole. When we look at a carbon double bond carbon, so that means one sigma bond and one pi bond, we have a bond strength of approximately 146 kilocals per mole. So that is showing us that the strength of the pi bond is going to be approximately 63 kilocals per mole. So the pi bond is 20 kilocals per mole weaker than a sigma bond. And this means that the electrons held in a pi bond are going to be more reactive because they're not as tightly held as those electrons in a sigma bond. So again, pi bond electrons are going to be more reactive. So when we look at our pi bonds, so our pi bonds are going to be our nucleophile. So what happens if we look at a general reaction? So we have our pi bond here, which again, this is going to be our nucleophile. We're going to have the addition of some electrophile. So most addition reactions involve two steps. So the first step is which a nucleophile is going to attack the carbocation. So the carbocation, again, is going to be the formation of that first step, like an SN1 reaction. So we would have something like this. So again, first step, like an SN1 reaction, and then what happens is our nucleophile is going to attack that carbocation. So we would have the addition of our nucleophile. So in the product, both the electrophile and the nucleophile are going to be bonded to the carbon atoms that were connected to that double bond. So if we look at the MO picture, the molecular orbital picture of this, what it's going to look like. So remember, when we have pi bonds, they have to be parallel to each other in order to form that pi bond. So we have our constructive, destructive. So again, they're parallel in order to form that pi bond. We have our electrophile, which again is going to be the vacant orbital or our lowest unoccupied molecular orbital. And what happens is, again, we're going to have an attack to form that carbocation in the first step. So that's going to give us this empty p orbital, which will be a carbocation. We have our electrophile attached. And then again, our nucleophile will attack this carbocation species. So remember, nucleophile is what's going to donate that electron pair. So if we look at the hydrohalogenation of alkenes, so hydrohalogenation of alkenes is really going to be addition of HX. So X is going to be our halogen, and we're going to look at alkenes reactions with strong acids. So if we look at, again, this alkene here, and we have the addition of a strong acid, what's going to happen is we are going to have H and X add across the double bond. So what that means is we're going to have something that looks like this. So our H and our X are adding across the double bond. So what happens first, we're going to look at the mechanism a few times in different ways. So first we're going to have protonation of the pi bond. So remember, protonation of the pi bond is going to be addition of the hydrogen. Then we're going to have attack by the halide. So this is going to be important when we're thinking of what type of product will form in different cases that we will look at. So we're going to look at a couple different additions that are possible. So the type of additions that we have are going to be the Markovnikov. I'll call this Mark just for short, but this is going to be a Markovnikov addition. So what this is going to be is this is going to occur when our halogen ends up on the more substituted carbon from the alkene. So if we look at the anti-Markovnikov, so anti-Mark addition, so this is going to be completely opposite. So this is going to place X on the less substituted. So we're going to go through both of these, Markovnikov addition and anti-Markovnikov, in detail. But if we look at a general scheme of that right now, if we have something that looks like this alkene, and say we're adding a strong acid to the alkene, what's going to happen is we have the formation of two different products. So we can have the formation of this product here, plus the formation of this product here. So again, this X is going to the more substituted, so this would be our Markovnikov addition. And then this halogen or X is going to the least substituted, so this would be our anti-Markovnikov addition. So again, we're going to go through the mechanism for both Markovnikov and anti-Markovnikov, and we'll look at different factors that kind of tell us which direction the addition is going to go in the next couple pages. So let's first look at stereochemistry of addition. So when we look at the stereochemistry of addition, we're going to have two different types. We're going to have syn addition and we have anti-addition. So syn addition is going to be when both H and our halogen, or X, are added to the same face. Whereas anti-addition is going to be H and your halogen are opposite faces of the alkene. So let's look at an example of this. So if we have this alkene here plus the addition of a strong acid, what we can have is we can have, again, addition of that HX across that alkene bond. So we could have the addition on the same face. So we could have this, which would be syn addition, plus the enantiomer of this. So H and X could be both behind. And we also can have the anti. So H and X are opposite faces, right? So one's pointing behind and one's pointing in front. Plus the enantiomer. And again, this would be our anti-addition. So this is also going to be important when we're looking at the different types of reactions all through chapter 8. So we will talk about if something is going to favor more syn addition or anti-addition, or if they're both can be both syn and anti products. So first we're going to look at the Markovnikov addition. So when we look at the Markovnikov addition, what this is going to be is this is going to be acid catalyzed addition of HX, so a strong acid. So this is also called direct addition, you may hear, or even ionic addition is sometimes used. So the main point of this is that we are going to have first protonation of the pi bond, like we talked about, and then we're going to have the halide attack that carbocation. So what we have to think about here is, since we're having the formation of a carbocation, we want to make sure that our carbocation that is formed is the most stable. So in order to form the most stable carbocation, that's why X is going to end up adding to the more substituted carbon. So let's look at that in detail. So again, if we look at this step right here, or this alkene right here, plus a strong acid, so we'll use hydrobromic acid, what's going to happen is we are going to have, so again, we're looking at Markovnikov, which means our halogen is going to go to our more substituted, So the bromine would go to this carbon because this is a tertiary, whereas this is a primary. So let's look at the actual mechanism for this, why this happens. So if we look at our alkene, so remember, you're going to be responsible for drawing maybe just the product, but you can also be responsible for writing out the mechanism for any of these reactions that we talk about in chapter 8. So when we look at the mechanism of this, we have our alkene plus our strong acid. So what's going to happen is we're going to have protonation of our pi bond. So we are going to be left with the formation of the carbocation, again, like an SN1 reaction. So this is why we really form the Markovnikov product, because when we look here, we can see that that carbocation is on, again, a tertiary carbon versus a primary carbon. So remember that carbocations want to be on tertiary or secondary, so something more substituted, just because it's going to stabilize that carbocation. So the more stable we can make the carbocation, the better the reaction rate, etc. And again, a carbocation is not going to be put on a primary carbon. So what will happen is we will have the formation, attack of our nucleophile, which in this case is going to be our bromine. So bromine is going to come in here now, and the halide or bromine is going to attack that carbocation. So what we're going to be left with is we are going to be left with this product here. So again, what product is not going to be formed is going to be that anti-Markovnikov, because when we're looking at the acid catalyzed addition, so the addition of a strong acid, when we're adding that H and X across that alkene, we know that we have to favor the Markovnikov, because this is, again, is going to be a two-step process. The first step is going to be the formation of that carbocation. In order for us to form a stable carbocation, because we have protonation of that pi bond first, we know that the halide attacks the carbocation second. So the more stable carbocation is what that halide is going to attack. And again, the more stable carbocation is just going to be the more substituted. When we look at the rate determining step, so again, we've talked about the rate determining step when we were looking at substitution reactions and elimination reactions, so specifically SN1 or E1 reactions. So we had that rate determining step as the formation of that carbocation intermediate. And again, the more stable carbocation will be favored because it's going to result in a faster rate. So if we look at the carbocation species, so looking at the species right here, we talked about this a little bit when we were looking at SN1 reactions and E1 reactions. So the carbocation intermediate is going to be planar because it's sp2 hybridized. So that means that stereochemistry of the addition, we can have both anti and syn addition. So for Markovnikov, we can have anti and syn addition. And again, the main reason for this is just because that carbocation intermediate is going to be planar. The addition of these reactions, so again, we specifically said that we're looking at strong acids. So what will work well will be hydrochloric acid, hydrobromic acid, hydroiodic acid. So hydrofluoric acid will work with these types of reactions, but the rate is going to be very slow. And the reason for this is, remember that HF bond is really strong because remember fluorine has the electron configuration of 1s2, 2s2, 2p5. So it's just very close to the nucleus, so it's just harder to break that bond. So one of the bad parts of these Markovnikov products, or kind of cons of these reactions, we have competition with other reactions, which I'm sure you could see because of the formation of that carbocation. So we're going to compete with elimination reactions. Another possibility that we have, which we looked at in chapter 6, with SN1 reactions, we have the possibility for carbocation rearrangements. So remember, if we have a reaction which occurs through a more stable carbocation, we will have a more stable transition state and it can be quicker. So that is something else that can lead to a lot of different formation of different side products, which is not ideal in a reaction. Another problem with these types of reactions, we are using strong acids, and depending on the alkene that we're working with, we could have a lot of different side reactions with the other functional groups in the molecule just because we are working with a strong acid. So if we look at the addition of anti-Markovnikov, so this is going to be free radical addition, which this should ring a bell from earlier chapter. So free radical addition, of HX, that's a really bad X. So HX, so this is going to be, again, the anti-Markovnikov addition. So when you hear anti-Markovnikov, what you should immediately think about is that the X, or the halogen, is going to go to the least substituted carbon atom in this case. So when we have a peroxide, so peroxide abbreviation is going to be this. So whenever you see a peroxide, this should automatically make you think of a anti-Markovnikov addition. You also will need some heat or light for these types of reactions. So if we look at this alkene here plus HBr, so again, we have that strong acid, but it's going to be in the presence of our peroxide in either heat or light. What's going to form is going to be the addition of our anti-Markovnikov, which again means that our halogen is going to go to the least substituted carbon atom, which in this case would be this carbon right here. So again, anti-Markovnikov. So we know that the product would not be this, for example, because this would be our Markovnikov product. So again, when we see that peroxide, we know that it's going to be an anti-Markovnikov addition. So when the peroxide is added, a halogen radical forms. So what happens is that halogen radical is going to add to the least substituted to generate a more stable carbon radical. And that's really the main reason why we have the formation of that anti-Markovnikov product. So let's go through the mechanism of this. So since you hear the formation of halogen radicals and things like that, I'm hoping that you are thinking along the chain of free radical chain mechanism. So remember, for free radical chain mechanism, we saw initiation, I think this was end of chapter 4, propagation, and termination. So we're going to be looking at all of these when we think of the mechanism of anti-Markovnikov. So if we look at our initiation, so remember, for initiation, we need to have the formation of a radical. So our first step in the initiation is going to be the formation of, again, we need heat or light. So we're going to have the formation of this radical here. And then what happens is we are going to have this radical is going to react with our acid, which in this case is going to be HBr, which we'll talk about at the end. And we are going to have the formation of our alcohol plus our bromine radical. So the reason that this is going to form is this is going to be more stable than the radical on an oxygen. So now that we have the formation of our bromine radical, what's going to happen is we're going to look at the propagation step. So second step for a free radical chain mechanism. So for the propagation, remember, we have the formation of a radical that we generated in the initiation step. We're going to react this with our alkene, and then we are going to have the formation of a new radical. So what's going to happen is we're going to have, again, mechanism, you're showing everything with arrows to show all flow of electrons. So this is going to form a tertiary radical as opposed to a primary radical because, again, the tertiary, putting a radical on a tertiary is going to be more stable. So again, this is the main reason why this reaction proceeds via anti-Markovnikov. So the next step that we're going to have is we're going to take this radical that we generated in the first step of our propagation. We're going to add it with our hydrobromic acid. And our bromine, again, is going to go to is staying on our least substituted, and our hydrogen would add where that radical was. Sorry, this looks like a really bad. There you go. So then we would have plus that bromine radical. So remember that in a propagation step, a radical always is generated. Otherwise, it would be considered termination. So termination is just going to be the addition of two radicals. There's tons of possibilities of this. I'll just show you one. So we would have termination here just because we have two radicals coming together. So when we're looking at the regioselectivity for anti-Markovnikov addition, the radical intermediate is going to allow, again, for both syn and anti-addition. So we can have both the bromine and the hydrogen on the same face or on opposite face. So there's a lot of different possibilities. So this reaction here is going to work only with hydrobromic acid. Again, when you have anti-Markovnikov, you have the hydrobromic acid. You're going to have a peroxide, which again, the peroxide is going to be shown as ROOR. And then you need heat or light. So the real reason that only hydrobromic acid will work is just because this has the right reactivity for each step of the free radical chain reaction to take place. The hydrobromic reaction also is going to be exothermic, which is also a factor that plays into why this works for these types of reactions. And again, if you really want to make sure for the rest of what we're covering and really all of Orgo 2, that you really understand the mechanism and why it's adding that way, and that will make the formation of the products make much more sense. So again, for anti-Markovnikov, we really are adding the bromine to the least substituted because we have to make sure that we're forming a stable radical. In order to form a stable radical, that radical has to be on a tertiary, ideally, carbon atom or a secondary, so something that's more substituted. When we look at the Markovnikov addition, so we have that first step, which is the formation of that carbocation. So again, the carbocation is going to be put on the more substituted carbon atom, so something like a tertiary, and then the attack of our halogen onto that carbocation is going to put our halogen on something that is more substituted. When we let's look at one example before we end this lecture. So let's look at this alkene here. We have hydrobromic acid, and then here we would have hydrobromic with our peroxide in either heat or light. So when we're going towards the left side, we have our Markovnikov addition. So again, we can have both syn and anti addition. And what's going to happen is our bromine is going to add to the more substituted, and our hydrogen would go to the least substituted carbon. So when we have our anti-Markovnikov, what's going to happen? So this is going to be that free radical chain halogenation. So we would have our addition of our bromine when we're looking at this alkene here on the least substituted. And our hydrogen goes to the more substituted. So again, here we're going to have syn and anti. So we'll have all four possible stereoisomers capable of forming in this instance too. So look over both Markovnikov and anti-Markovnikov reactions. Again, really make sure you understand the mechanism in order to understand what's really happening. Work on the drill problem that will be due after Chapter 7 quiz. And if you have any questions, reach out to me. There's going to be a lot of reactions that we're going to be looking at in Chapter 8, so I would try to stay on top of the reactions as much as you possibly can. I hope you all are doing well, and please reach out to me with any questions. Have a great day, everyone.